So let's define elements first. So on the left we have an element name, and then we have how it occurs in nature in this box. Again, these are particles. If they're next to each other like this, they are bonded. So, for instance, if we wanted to know what elemental bromine is, we could look at this picture and we would say we have two bromines. So we could write the elemental symbol for bromine, which would be Br, and then write a 2 next to it, so Br2. This is helium, there's just one of them, so we could just write an He for helium, and then this is aluminum. It has a lattice structure, so we would just call this solid aluminum, right? Because this could repeat forever. That's the interesting thing about lattices. They can just keep going on as long as you have materials. But elements, let's get sort of a definition here. Each is made of only one type of atom, right? We can see that in all of these examples. Just bromine, just helium, just aluminum. The primary constituents of matter is what an element is, right? So they can't be chemically broken down into simpler substances. You may know that there are smaller things than an atom, but those are fundamental building blocks, and they don't have the same properties as elements. Elements are really what we're going to be concerned with in this class mostly. And then the name of the element substance is typically the same as the names found on the periodic table. There are some exceptions, some isomers and isotopes that we'll talk about. But for the most part, if you see helium on the periodic table, we will just call it helium. All right. So here is a picture. You can see the name of the element and the symbol. There is a name for all of the elements, and they each have a corresponding symbol. Oftentimes we will just use the symbol because it's much quicker to write. And as we put more and more things together, then we will not want to have to write all this out, right? So here is a fun video of Daniel Radcliffe singing The Elements. I want you to see if you can figure out how many elements there are on the periodic table.
Give a big shout if you know who Tom Lehrer is. Yes. People know Tom Lehrer.
Yes, so over there, yes, they couldn't be more excited.
Okay. So Tom Lehrer, in my opinion, is the cleverest and funniest man of the 20th century, and he's kind of my hero. And he wrote a song called The Elements, because he was a scientist, and it's the name of every element in the periodic table. And that's my party piece. It's quite long, so do stop me if you just get bored.
Okay.
But I will. This kept me up last night. I was so nervous about doing this.
Well, do I feel bad now?
No.
Okay, so.
There's antimony, arsenic, aluminum, selenium, and hydrogen, and oxygen, and nitrogen, and uranium, and nickel, neodymium, neptunium, germanium, and iron, americium, ruthenium, uranium, europium, zirconium, lutetium, vanadium, and anthium, and osmium, and acetine, and radium, and golden protactinium, and indium, and gallium, and iodine, and thorium, and thulium, and thallium. There's yttrium, and terbium, actinium, rubidium, and boron, gadolinium, and opium, iridium, and strontium, and silicon, silver, and barium, bismuth, bromine, lithium, beryllium, and barium. And let's start the next verse. There's holmium, and helium. There's holmium, and helium, and aphium, and erbium, phosphorus, and francine, and fluorine, and terbium, and manganese, and mercury, and molybdenum, magnesium, dysprosium, and scandium, and cerium, and cesium. There's lead, praseodymium, platinum, plutonium, palladium, promethium, potassium, polonium, and tantalum, technetium, titanium, tellurium, and cadmium, and calcium, chromium, and curium. There's sulfur, californium, and fermium, berkelium, and also mendelevium, isinium, nobelium, and argon, radon, neon, and argon. Hold on, quiet. There's sulfur, californium, and fermium, berkelium, and also mendelevium, isinium, nobelium, and argon, radon, neon, krypton, xenon, zinc, and rhodium, and chlorine, carbon, cobalt, copper, tungsten, tin, and sodium. Now,
There you have it. All the elements. So if you're counting carefully, there are 118 elements on the periodic table. And we have discovered elements very recently, actually. So it's possible you could discover an element. And there'll be an activity at the end of this that kind of talks about that. Here is a periodic table of the elements. We will learn this very well as each of them. It is organized in a very specific way to help give you information. Of course, the first couple times you look at it, it might be a little overwhelming. There's lots of things on there. But we will get through it. We will learn how to navigate this. You can see right there, like atomic number, the symbol, the name, its mass, And then there's all these different colors to identify different groups. And each group kind of has its own set of properties. You may recognize some things on here. Copper, silver, gold, right? Carbon, oxygen. These are the building blocks of everything. So let's talk about compounds. We know what an element is, right? The smallest thing that can't be broken down anymore without compromising those chemical properties. But compounds, let's think about what are compounds, right? Let's first identify perhaps a formula for each of these, right? So water is made up of two H's, two hydrogens, and one O. So its formula would be H2O, right? Sodium chloride, which is just table salt, is made up of one sodium atom for every one chlorine atom. So these lattice structures, yes, they can repeat forever, but when we're identifying them, we're looking at the fixed ratio, right, between these, which would be 1 to 1. For every one green, there's one blue. This methane is made up of one carbon and 4 hydrogens, so it would be C for carbon and H for hydrogen, CH4. So compounds contain atoms of different elements chemically bonded together. And they are always bonded in fixed ratios, right? So for water, there's one oxygen to 2 hydrogens. For sodium chloride, there is one sodium for every chlorine. For methane, there is one carbon for every 4 hydrogens. Excuse me. And so remember, like, 2 elements of the same thing bonded together are not a compound. They are a molecule, but not a compound. They have to be different elements, right? And thinking about the differences, right? We have these things arranged in different ways. These would be like a molecular compound, because we have the compounds all kind of next to each other. Same thing here, and this would be a lattice compound, right? Organized and repeating. So that's important to know. Molecular, lattice, both are compounds. And yeah, again, in a molecular substance, a specific number of each atom is required, right? 2 to 1. But in the lattice, you can repeat for as long or as little as happens. So here are some compounds. There are millions of compounds, seemingly endless amount of compounds. Sodium chloride is table salt. Magnesium hydroxide, that is a base, right? Water, you drink this every day. Methane is a gas that is flammable. Glucose is something that your body uses for energy, right? Sulfuric acid. Each of these has a formula, right? Na is sodium, Cl is chlorine. For every 1 sodium, there's 1 chlorine. Each of these is a fixed ratio of the elements. And we will get really good at writing chemical formulas together. So we know what elements are. We know what compounds are. What about mixtures? What are mixtures? So we have 2 different mixtures here. On the left, we have air. Yes, like the air you breathe. And on the right, we have 2 different types of steel. And I want you to think about the similarities, right, between these 2 things. What similarities do you see between these 2 mixtures? So they both contain a number of elements, right? Each color is an element, right? Air has these different compounds, whereas steel has these, it would be iron and carbon, right? Air would be like nitrogen and oxygen and argon, and even some CO2 is in here. The components of a mixture do not require a fixed ratio, which you can see in these, right? There's no specific ratio to how these things are mixing together. Maybe you add a little bit more CO2, or we have a little bit more oxygen, or in this steel, one of these has less carbon than the other. So a mixture contains more than one element or compound in no fixed ratio, and they are not chemically bonded. And the components of a mixture can be separated by physical methods. So we're going to learn about all the ways we can separate a mixture. But this is what's important. Contains more than one element or compound, right? And here it's just two different elements, and here it's elements and compounds. There's no fixed ratio, and they are not actually bonded to each other, right? CO2 is not bonded to O2. In this one, it's kind of confusing because they're all sitting next to each other, but these things are not actually chemically bonded to each other. And that's something that can happen when you're mixing metals with things. They can incorporate other things, but not necessarily be chemically bonded together. Okay, so here is some examples of mixtures. So air, right? It's full of lots of things. The two most prominent things are nitrogen and oxygen. And it has this interesting part in the table, particle interaction 1 and interaction in mixture. So this is basically saying what are the forces that are acting on the components within the mixture. So in the case of air, there are dispersion forces, so that's just like a light amount of the electromagnetic force acting on these things. They are very lightly attracted to each other, right? Another mixture is bronze, which you might think of as like a metal. It is a mixture of metals, which has copper and tin in it, and they both have metallic bonding going on, and when they're in a mixture together, they also have some metallic bonding interactions. And then there's salt water, which is a mixture of salt, NaCl, and water, right? NaCl is held together by ionic bonds. Water, it hydrogen bonds to itself, which we'll talk about if you don't already know. And so when these two things interact with each other, they have an ion dipole interaction, which basically there is an ion in the salt, and it is attracted to a partial charge on the water, and so they interact